Welcome. This question says a 10 Coulomb positive charge is located at the origin using the method of Gauss law shown in class. Determine the electric field at any point that is 3 meters from the point charge. So let's visualize first of all. Let's remind ourselves in physics we have x-axis, y-axis and z-axis, and my 10 Coulomb positive charge is at the origin, so let's do that there. And then I'm imagining a point which is 3 meters away. It does not really matter. I'm going to put the point there. There's my point P, and I need to find the electric field at the point P. I can represent the electric field by a vector E. This is a positive charge, so if I imagine putting a positive chest charge at P, the vector will point away. The method of Gauss's law, as shown in class, involves constructing a Gaussian surface, a closed Gaussian surface. And there are good Gaussian surfaces for any given problem, and there are not so good Gaussian surfaces for any given problem. And a good Gaussian surface is one whose symmetry enables me to simplify my math. Now, because I've done this before, I happen to know that a good Gaussian surface for this problem is a spherical Gaussian surface, which is centered on this charge. So I'm going to show this. I can't draw a sphere, so I'm going to draw the circle of the sphere like that. So that's my Gaussian surface. And I'm going to imagine dividing this Gaussian surface up into a whole bunch of little windows, and through each window I'll get an electric field, and through each window I will get an area, from each window I'll get an area vector. Now remember, the area vector is a vector. It's an imaginary vector which is perpendicular to the glass in the window. It points outside the enclosed volume. And I'm going to basically integrate over this entire surface. What makes a good Gaussian surface? A good Gaussian surface is one that helps me mathematically, and the typical things I look for is, can I imagine a Gaussian surface which has a constant electric field over its entire surface, or regions of the surface? That's one good thing. Is the electric field parallel to this little area vector? That would be good. Or if it was perpendicular to the area vector, it would be good. But you don't want it varying with each window. And so there's two good rules anyway to be thinking about. So basically, let's remind ourselves of what Gauss's law is. And Gauss's law says that the flux is equal to the integral of E dotted with dA, which equals Q inside over epsilon naught. Let me mark on here, the radius of course is, we're going to call it R. We'll do the numbers later. So then I can turn around and say, okay, well my flux, let me So what I notice for this Gaussian surface is that E is constant over the Gaussian surface. And I know that because it's always the same distance. If you're the same distance away from a charge, then all points on that sphere will have the same electric field. So it becomes a constant, which is a good thing when I'm integrating. And then the second thing I notice is that E is parallel to dA over the entire Gaussian surface. And what that means is, when I expand this, E dot dA equals E times dA times the cosine of the angle between them, and because the angle between them is 0, cosine of 0 is 1. So again, it simplifies my math. So then I can say, well, under those circumstances, my flux is equal to E integrated with dA. It's just a nice way of going from something that could be quite complicated to something that's much more straightforward. And that equals Q inside over epsilon naught. Now, the next thing that I realize is that, oh, this is a sphere. So the integral of dA, all the little windows added together throughout the surface, must equal 4 pi r squared. R, of course, is the radius. So, okay, then E times 4 pi r squared is equal to Q inside over epsilon naught. I want to find just E, so E is equal to the Q inside over 4 pi r squared times epsilon naught. I'm almost there. There's a little nicety, which is that I remember that Ke is equal to 1 over 4 pi epsilon naught. This does not change the answer, it just changes the form of the answer. This is like a nicety. And so when I substitute that in, I get E is equal to, well, 1 over 4 pi epsilon naught gives me Ke times Qn over r squared. Now, we learned before when we did basically electric force and electric fields that the electric field at a certain distance from a charge was equal to Ke Q inside Q. We're calling it Q inside now because it's the inside the Gaussian surface, but it's Q, whatever Q is there, over the separation squared. So we've just confirmed an equation that we already knew. And you might say, well, why are we doing this? And the reason is we're learning a technique. We're going to apply this technique to systems that are not as obvious as this. So it's a good thing. And it's also we're confirming something. We did the analogy to Newton's work on gravitational fields to get this original value, original equation, and now we've approached it with another technique. So then we turn around and say, let's put some numbers in. So E is equal to 9 times 10 to the 9, that's my Ke. Again, in a test, I'd be okay with you leaving the Ke in, I'd quite like it actually. And then Q in, the Q inside is positive 10 coulombs, so we'll put down plus 10 over, and my R is 3 meters, so that's going to be 3 squared. So that's going to be 10 times 10 to the 9. Let's do that again. Is that right? Yep, which equals 1 times 10 to the 10. And the units are going to be newtons per coulomb because it's an electric field. So on a test, when I say using the method of Gauss's law as shown in class, this is what I'm looking for. I'm looking for a good diagram. I'm looking for Gauss's law to be stated. I'm looking for good justifications for making the mathematical transition, justify taking E outside, justify that dot product not having to have an angle inside it. And then I want to see that you remember, oh yeah, the area of a surface area of a sphere is that value. And then substituting in, I want you to remember that Ke equals 1 over 4 pi epsilon naught. These are things we need to know. So I expect to see all of that. If I say just figure out what the electric field is, you can use the equation that we learned in the previous chapter. When I say using Gauss's law, I want you to show me all this. So there we have it.